inertia. Okay, so in the previous class we have seen what is angular momentum. What is angular momentum of a body? It is nothing but the moment of the linear momentum of body. Okay, therefore a linear momentum is what is called angular momentum. Okay, therefore angular momentum is represented by L, and L is nothing but moment of the linear momentum, that is R cross P. This we have seen, right? Now we are going to see how what is the relation between the angular momentum and moment of inertia. Okay, for that, let us consider a body which is rotating here about an axis, that is AB, okay, with a uniform angular velocity, that is omega. Okay, let me take two, that is m1, let m1, m2, m3, okay, m2, m3, etc. up to mn are the particles. Okay, the body contains n number of particles, consists of n number of particles, and the mass of particle, let it be m1, m2, m3, m4, etc. up to mn. Okay, only sample particles I have taken. So, and these particles are at a distance of R1, perpendicular distance, R1, R2, R3, R4, etc. up to n number of particles up to Rn. Okay, therefore here R1, R2, R3, etc. up to Rn are the perpendicular distance of those particles, respective particles, from the axis of rotation. Okay, therefore now because though their angular velocity is same, okay, the linear velocity, you know that definitely it will change. Why? Because V, that is equal to R into omega. Therefore, see, omega, though omega is constant, different particles are at a different distance from the axis of rotation. Therefore, definitely the linear velocity will be different. Okay, therefore let okay, V1, V2, V3, etc. up to Vn, okay, they are the linear velocities of the particles, the first, second, third particles, that is up to nth particle, that is nth particle, okay, which are different. Why? Because their distance, perpendicular distance from the axis of rotation are different. Is it clear? Therefore, how can you write therefore V1 that is equal to R1 omega. Omega all are having the same angular velocity, because every particle will, as the whole body, it rotates, so completes one rotation about the axis AB. Every particle, constituent particle, they complete their own circular path of different radii. Okay, therefore the angular velocity of each and every particle is the same, that is equal to the angular velocity of the whole system. Okay, therefore that is given by omega. Therefore, but what is the linear velocity? As linear velocity definitely differs, because their perpendicular distance V is equal to R omega. From that relation, you know very well what is the linear velocity for different particles will be different, because they are at different distances from the axis of rotation. Okay, etc. Vn that is equal to Rn into omega. Is it clear? Right. Therefore, this is about the linear velocities of the particles. Okay, or all the particles. Right. Now, what is the linear momentum of the particle? Therefore, the linear momentum of first particle. What is the linear momentum of first particle? Let it be P1. Okay, that P1 that is equal to, you know, linear momentum is nothing but M1 V1. Therefore, what is M1 V1? That is equal to M1. What is V1? R1 omega. Are you following? Therefore, it is, this is nothing but the linear momentum of the first particle, right? Therefore, now I want angular momentum now. Therefore, what is the angular momentum of the first particle? Therefore, the angular momentum of first particle, okay, about the given axis, that is very linear momentum, and angular momentum of the first particle about axis क्या है? axis AB. Here also about axis AB. That is this axis, okay? Given axis, whichever axis you have taken. Therefore, that is nothing but, what is the linear momentum? Linear momentum is P1. What is the angular momentum? Angular momentum is nothing but moment of the linear momentum. Okay, that is nothing but, okay, this P1, R1, P1. Hai na? Are you following? Because what is the R cross P? It is nothing but angular momentum. Okay, therefore here, what is your angular momentum here? Angular momentum is equal to, what is that? R1 P1, and that is nothing but, okay, that is nothing but, what is that here? That is nothing but M1 R1 into M1 R1 omega. Okay, and what is that? That is nothing but, okay, M1 R1 squared omega. This is the angular momentum of the first particle. Let me give name as L1. That is L1. Okay, right. Therefore, similarly, you can say that angular momenta of other particles. This first particle, for all the other particles about the axis AB. That is given by L2, that is equal to M2 R2 squared omega. L3, that is equal to M3 R3 squared omega, etc. Ln, that is equal to Mn Rn squared omega. That's it. Therefore, now you have the angular momentum of each and every particle about the axis, that is AB you have. Okay. Now, but what I want the angular momentum of the whole body. Therefore, okay, therefore I can say angular momentum, the angular momentum of the body. It is not a particle of the whole body, of the whole body, okay, about the axis AB. Okay, and that is nothing but L. Okay, what is L? It is the sum of the linear momentum of all the particles. It is a sum of linear momentum of all the particles. What do you mean by that? It is sum of angular momentum of each and every particle. There was some. What is the moment of linear momentum? Is angular momentum. As I told you, what is this? It is nothing but the total angular momentum of the whole body is nothing but sum of the moment of linear momentum of all the particles about that axis AB. Or in other words, it is nothing but the angular momentum, sum of the angular momentum of all the constituent particles. Therefore, I can say that it is L1 plus L2, etc. Ln. Okay, therefore, that is nothing. That is L, that is equal to, what is L1? L1 is equal to M1 R1 squared omega plus M2 R2 squared omega plus M3 R3 squared omega plus etc. Mn Rn squared omega. That is it. Therefore, your angular momentum can be written as, okay, this M1 R1 squared, M2 R2 squared, M3 R3 squared. Therefore, I think that I can write as sigma I, that is equal to 1 to n Mi Ri squared. Okay, therefore times omega. Okay, therefore now I think you know what is this factor. Sigma I, that is equal to 1 to n I r I squared is nothing but your moment of inertia. This is nothing but the moment of inertia of the body, whole body, about the axis AB, because moment of inertia I told you about which axis is very important, about that axis, that is AB. Therefore, you can give, therefore, what is the total angular momentum? L, that is equal to I into omega. L, that is equal to I into omega. So this is how, what is the angular momentum and moment of inertia are related. L is equal to I omega. Is it clear? Therefore, you can say that it is nothing but what is the angular momentum of a body about any axis is the product of moment of inertia and angular velocity of the body about that axis. Okay, therefore, I think from this you can give one more definition for moment of inertia. Moment of inertia, how? When omega, that is equal to 1 radian per second, I, that is equal to L, I is equal to L. That's all. That gives you one definition. What is that? The moment of inertia of a body about any axis is numerically equal to the angular momentum of the body, which is rotating with unit angular velocity about that axis. Okay, therefore, what is that? The moment of inertia of a body about any axis is equal to the angular momentum of that body, which is rotating with uniform angular velocity about that axis. Okay, right. Therefore, you know very well now, angular momentum, that is equal to I omega, you know, which is very much similar to your linear momentum. What is linear momentum? P, that is equal to, what is P is equal to M into V now? M into V. Okay, therefore, listen very carefully. Therefore, in the place of, what is that, M, see, in the place of V, linear velocity, angular velocity is there. In the place of mass in linear motion, what is mass here is replaced by moment of inertia. The role played by mass in linear motion is played by moment of inertia in rotational motion. Okay, in rotational motion. Therefore, mass and moment of inertia are, what is that? They are analog. Let's see, what is the analogy? Mass in linear motion is replaced by moment of inertia in rotational motion. That is why you know that what is linear velocity? Linear kinetic energy. In linear kinetic energy of the body which is moving in a straight line path is half mv squared. Okay, but what is the rotational kinetic energy? What is the rotational kinetic energy? That is equal to half, okay, I omega squared. Already we have derived it. Okay, therefore in the place of M, what is there? I is here. Okay, and V is replaced by, of course, linear velocity replaced by angular velocity, and M, wherever M comes, you have to replace it by moment of inertia in rotational motion. That's it. Very simple. Okay, therefore, now what is the relation now? Let me have, that is relation between torque and angular momentum. Very simple. Angular momentum. Okay. What is it? You know, just now we have seen what is the L, that is equal to linear momentum, angular momentum is equal to I into omega. Okay. Therefore, if I differentiate it, okay, if I differentiate, then you will be getting dl with respect to time, dl by dt. dl by dt, that is nothing but, dl by dt is nothing but I into d omega by dt. d omega by dt. Okay, and that is nothing but I alpha. Are you following? Therefore, this I alpha, what is it? This I alpha is nothing but, okay, torque. It is nothing but torque. I alpha is nothing but torque. Okay. Well, how there is, see here, why? Because I alpha is equal to torque. How? It is nothing but so I alpha is equal to torque. That actually, that gives you the relation between torque and moment of inertia, right? Torque and moment. Torque is equal to I into alpha. So if you want, we will derive now, but though it is just within 2-3 steps, I'll give you the how torque and moment of inertia are related for that. Okay, let me, because a body which is actually moving, rotating about an axis AB, and but here with a uniform angular acceleration. Uniform angular acceleration. Okay, the body here, it is what are all the constant particles? Okay, M1, M2, M1, M2, M3, M4. Okay, all the particles that is they are at a distance, that is R1, R2, R3, R4 from the axis of rotation. Okay, because the particle, the full body is rotating about a uniform, not angular velocity, angular acceleration. Angular acceleration. Therefore, okay, the angular acceleration of each and every particle of mass M1, M2, M3, everything will be the same. But angular acceleration, okay, therefore the angular acceleration of each and every particle will be alpha only. But what do you say about the linear acceleration? You know that how angular acceleration, linear acceleration are related. Angular acceleration, linear acceleration related as, that is, what is our linear acceleration? A is equal to R into alpha na? Already we have seen. Therefore, so A, that is equal to angle, linear acceleration is equal to, what is that? R into angular acceleration. Therefore, definitely, now your angular acceleration of each and every particle will be different. Why? Because they are at different distances from the axis of rotation. Though they are having same angular, though all the particles are having same angular acceleration, the linear acceleration is different for different particles. Why? Because linear acceleration is equal to R times alpha. Here R for different particles are different. Is it clear? Therefore, see, the body is rotating with a uniform angular acceleration alpha. So each and every particle constituting the body will also have the same angular acceleration. But the linear accelerations are different. That is A1, A2, A3, etc. up to AN. Okay, therefore, is it clear? Therefore, because each and every particle is having some acceleration, definitely there is some force that is acting. You know that the body will not get accelerated, the particles will not get the acceleration unless there is some force. Therefore, you can say each and every particle is having an acceleration. Therefore, each and every particle will be acted upon by a force. Okay, therefore, force on first particle. Okay, let it be F1, that is equal to M1 A1. Okay, that is equal to M1. Okay, A1 is nothing but R1 alpha. Okay, like that, force on second particle F2, that is equal to M2 A2, that is equal to M2 R2 alpha. Is it clear? Therefore, now force I know. Therefore, okay, therefore they are having some angular acceleration. No, all the particles are having some uniform angular acceleration. There is some angular acceleration, means definitely torque is there. Without the torque, see, without the force acting on the body, there will not be linear acceleration. Like that, without the torque acting on the body, there will not be any angular acceleration. But here each and every particle is having a uniform acceleration, that is alpha, which means that there is some torque that is acting. Okay, therefore, what is the moment of force? Torque is nothing but moment of force. Therefore, moment of force, Okay, moment of force about of first particle about axis AB. That is nothing but, okay, moment of the linear, moment of force is nothing but torque, na? Therefore, that is nothing. What is the moment of, see here, force is this, okay? Therefore, R1 cross F1, R1 into F1. Therefore, what is R1? R1 into F1 is nothing but M1 R1 alpha. M1 R1 alpha. Is it clear? Therefore, now you tell me that is nothing but, okay, it is R1. Okay, therefore M1 R1 square alpha. This is for first particle. Therefore, moment of force of second particle. Therefore, moment of force of second particle, that is equal to M2 R2 square alpha. Therefore, moment of force of nth particle, that is Mn Rn square alpha. It is moment of force of nth particle about axis AB. Okay, that is equal to this. Right. Now what I want is the total moment of force of the body. That is nothing but torque acting on the body. Therefore, torque acting on the body. It is for each and every particle. Now torque acting on the whole body. Acting on the body about axis AB. That is nothing but sum of the moment of forces acting on all the particles about the axis AB. Sum of the moment of forces. Okay, that is, see, moment of force of each and every particle, you know, if you sum everything, then you will get the total moment of force of the whole body. Total moment of force of a whole body is nothing but torque. Okay, therefore, torque acting on the body is nothing but sum of the moment of forces of all the particles of the body about the axis, that is AB. Okay, therefore, that is nothing but M1 R1 square alpha plus M2 R2 square alpha, okay, plus etc. Mn Rn square alpha. Okay, therefore, what is the torque acting on the body about AB? That is equal to, okay, sigma I, that is equal to 1 to n mi squared alpha. Once again, what is mi squared is nothing but sigma I is equal to 1 mi squared is nothing but moment of inertia. Tau, that is equal to I alpha. Tau is equal to I alpha. Is it clear? Why? Because I cannot write, because I have written here I alpha, that is equal to tau, I told you, no, so I have given you derivation. Okay, therefore this, actually this derivation is nothing but what is the relation between whatever we have now seen between torque and I, moment of inertia. Are you following? So that I am writing here tau I alpha is equal to tau. Is it clear, children? Okay, now what we want, now once again we will go back to the previous one. What is the relation between torque and angular momentum you want? Therefore, from this what you have dl by dt, that is equal to, what is that, torque. dl by dt is nothing but torque. Is it clear? Therefore, very, very important. Therefore, now, see here, just now, what is that? Torque, that is equal to, so you can say torque, that is equal to I alpha, that is nothing but, what is that? I into d omega by dt. Alpha is d omega by dt, and that is nothing but, okay, that is nothing but, what is that? That is nothing but dl by dt. That is nothing but dl by dt. Is it clear? L is equal to I omega, na? L, that is equal to I omega. Therefore, is it clear? Tau is equal to I alpha is equal to dl by dt. So, now, Let us compare it with our linear motion. Because torque, wherever torque is there, it is replaced, there is a analog to force in linear motion. And moment of inertia. Moment of inertia means mass. In linear motion, the role played by moment of inertia, rotational motion is played by mass in linear mode, right? It is angular acceleration, though linear acceleration ho jayega. Therefore, F is equal to ma. It is Newton's second law of motion. The same Newton's second law of motion here, and tau, that is equal to I into alpha. Both are similar. Here it is linear motion, here it is rotational motion, that's all. Okay, and once again you know F, that is equal to, here you see torque, here is equal to dl by dt, na? Therefore you know F, that is equal to dp by dt. dp by dt, second law of motion, na? F is equal to dp by dt. P, what is that P? Linear momentum. Here what is L? Angular momentum. Rate of change of linear momentum is force. Like that, rate of change of angular momentum is torque. That's all. Rate of change of angular momentum is torque. So it is Newton's second law in rotational motion. That's all. It is Newton's second law in rotational motion. Rate of change of angular momentum is nothing but torque. Clear? Okay, right. Now, therefore, from this, therefore, very, very important. Now we are going to see already you people have idea about it anyhow. So principle of conservation of linear angular momentum. Angular momentum. Principle of conservation of angular momentum. Okay, therefore, consider the total angular momentum of a body. See, consider according to this principle, what is that? When there is no external torque acting on a system of particles, or acting on a system, then the total momentum of the system remains constant. Okay, therefore, say so here, rotational motion. Rotational motion is here. In a system, a rigid body means it contains so many number of particles. Okay, therefore it is nothing but combination, that is, it is collection of so many particles, nothing but what is a system. Therefore, when no external force is acting on the system, then the total angular momentum of the system remains constant. Therefore, you can say tau total. That is, if I see here, just I have given you all in a vector, not a vector notation. If I want a vector notation, means just everywhere you have to put. Okay, dl by dt, like that. Okay, right. Therefore, tau total, that is total torque acting on the body, is nothing but, what is that? Rate of change of total momentum of the body, angular momentum of a body, dl by dt. Okay, therefore, when torque, total torque acting on the body, total torque, why total torque? Each and every particle is having some angular acceleration. Therefore, every particle is having moment of force. If you sum up all the moment of the forces, then only here we have taken. See, if you sum up all the moment of forces, only then you are getting the total torque acting on the body. Okay, that is why here, when total torque that is equal to 0, okay, you can say that dl total, that is rate of change of angular momentum, that is equal to 0. Therefore, you can say L total, that is angular momentum of the body. That is nothing but the sum of the angular momentum of all the constituent particles. Already we have seen. Okay, and that is equal to constant. Why? dl, are you following? Therefore, it is tau. Okay, d tau total by dt is equal to 0 means, which implies your tau total is constant. Differential of constant quantity is only 0. Therefore, if tau total is constant means if you differentiate, that has to be equal to 0. Hai. Therefore, what is tau total? Tau total is nothing but what is the sum of the angular momentum of the constituent particles about that axis. about that axis is very, very important, about which axis it rotates. Okay, so it is very important. This is nothing but the principle of conservation of angular momentum. In the absence of an external torque, the total angular momentum of the body's system of particles remains constant. Total angular momentum of a system remains constant. Is it clear? Therefore, if external torque is equal to 0, then angular momentum, okay, of the body system remains constant no matter what changes takes place within the system. Within the system, whatever change takes place, it won't bother. Okay, therefore, why? Because the angular momentum, okay, bothers only about the total external, that is torque, that is acting on the body. Whatever is changes are taken within the system, no, the angular momentum won't bother. Okay, therefore, angular momentum, see, which means that you can say that when tau that is equal to 0, L is a constant. L is equal to constant. Okay, that is, what is L? L that is equal to I into omega, na? L is nothing but I into omega. I is nothing but C, that is P, that is equal to M into V, linear motion. Like that angular momentum, it is linear momentum. Angular momentum is I into omega. Therefore, that is, this we have seen, L is equal to I omega, that is a constant. Is a constant. Is it clear? This is conservation of angular momentum. In the absence of external torque, the total angular momentum of a body, of a system of bodies remains constant. Okay.